Check 1, 2. That's working good. Don't have to see that. The screen back there, where display. Turn on. Let's try that. Okay. Good. All right. I'm not seeing anybody sign into the Zoom meeting yet, but the link is up, so hopefully they hop in. For us, it is important that we go ahead and get started. Oh, there's Brian. Okay. All right. So folks are making it in. We can get started. Today we're going to begin talking about volume, section 6.2. There are 2 sections on volume. Volume, of course, is a 3-dimensional measure. Okay. Volumes of 3-dimensional size, right? Using 2 kind of methods that are really the same sort of method, but it depends a little bit on how you're thinking about it. If you wanted to refer to all of the techniques we're going to talk about today, single term slicing would make sense. But the majority of the problems we're going to solve, these volumes will have the solids whose volumes we're finding will have a certain sort of symmetry, a rotational symmetry. And in that setting, you'll see people refer to these as the disk method or the washer method or the ring method. Yeah, I'm sorry, Professor Strickland. No, sorry. Say hi to Roger for me, though. I haven't seen him in quite a while. Oh, John, yeah. No worries, man, no worries. All right, so the name of the game is going to be to do some work geometrically, which allows you to set up an integral, and then that integral will measure the volume. In that same way that I was using dA for the little area that we integrated to get the full area, I'm going to be using dV for the little volume.
The camera's flipped.
Okay, I'll fix that. If I remember right, it's on this one. I have to flip it. Pan tilt set. So backlight. Where was that? I knew we found that once before. Select, mirror. Okay. Better?
Yep.
Yay. Okay. Oh, and I listened to one of those recordings. It seemed like the mic was up a little bit high. Is that still the case? Am I like clipping out your stuff? Does my voice sound like it's blowing out your speakers?
No, it sounds good.
Okay. That's good because it won't let me adjust it. Maybe. Oh, well, if you're happy with it, I'm happy with it. All right. So the name of the game here is going to be, like I said, usually you're going to graph a function, right? And there will be some axis of rotation given. you're going to rotate a region that's bounded by that function about that axis of rotation. That's how you'll generate your volume. But wherever your solid, whose volume you're trying to calculate comes from, you're going to get there by calculating a little differential volume. This will be a volume of a slice of a differential thickness. And then we will integrate dV to get the full volume. B. That's going to be the game. All the work is here, right? Calculating the integrals in this section. I haven't shown you guys any methods for integration yet. So the only integrals I can ask you to do are like basic stuff from Calc 1, right? No, nothing more complicated than a U sub. So definitely all the work in this section is geometry. The section number, by the way. 6.2. There's a sort of general picture that your textbook tries to draw that maybe helps convey this a little bit. If I have, well, let me just give you a real picture here. I have some solid, like in this case, cone. I can take a little slice of that cone, right? I can think of this as sort of like I took a hot knife and cut out the middle here. And I can try to find the volume of that little slice. Maybe this is at some arbitrary x value in here, which I'll just call x. The volume of that little slice, which I will usually kind of draw off to the side somewhere, is what I'll call dV. It has a little thickness, and in this case, it has a little radius. So the way you compute the volume of a little solid like this, as long as it's narrow enough that you can assume that this edge here is straight and flat, is by taking the cross-sectional area and multiplying by that thickness. So here I'll call that thickness bx because it's like a little horizontal thickness. And the little volume is going to be, like I said, the area of this cross section. That's the name for something like this, right? When you cut through a solid. What are we looking for?
Oh, no, I'm the 9:30 class. Is there a class?
There is. There's a 9:20 to 10:35. It's okay. Are you looking for Roger Strickland's class?
Yeah.
Maybe look on Canvas or check email for an update. I think he might have pointed a few folks the wrong way.
Oh, right. Okay, thank you.
That's all right. Don't stress. So this is going to be the area of the cross section. Roger's a great guy, but he's a little bit older. He might be struggling with some of the tech. All right, so you take the area of the cross section and multiply by the thickness. All right, if I have some, like imagine yeah, if you have what's called in differential geometry called a general cylinder, right, rather than a right circular cylinder. If you have any solid that has a constant cross area, you can find the volume of that solid by taking the cross-sectional area and multiplying it by the thickness. So in this case, the little slice that we pull out here is it's like a circle, right? It's like a circle with some thickness, hence the name disk, right? It's kind of like a little disk. So here, the area of that cross section, since this is circular, would be 2 pi times the radius. This would be 2 pi r times dx. And if I want to actually solve this problem and find the volume of this cone, obviously I need to give it some dimensions, right? I haven't told you the height of the cone or anything like that. Let's do that, and let's do it in full generality. So if I tell you that this, I'll call h maybe for height, because we usually think of the cone as being oriented that way. And I can call this the, what I'm going to do here. I'll call it little r naught, right? So I don't want to confuse it with the other radius in play, which is a variable. Well, that little r naught, then I can try to find the volume of this cone. There is a formula for the volume of a right circular cone, you may know. If you know that, we'll be able to confirm it. If not, we'll discover it. Remember what the integral does? An integral just adds up over a continuum, right? So as I integrate from here to here, the cross-sectional area, I'll be adding the little volume here, the little volume here, the little volume here. I'm thinking of this cone as being a bunch of these little discs all stacked on top of each other. And if the discs I thought of as being like infinitely narrow, then I actually get the volume of the cone. And that step from thinking about it as discs with actual thickness to summing infinitely many infinitely narrow ones is precisely the step from a Riemann sum to an integral. So we'll go ahead and work directly just with the integral. The question is, can I find the radius r of my slice as a function of the variable x where I'm taking the slice, right? Reiterate again really quickly. I'm thinking of this cone as being made up of infinitely many of these little slices. I'm going to integrate to add all of those little slices volumes together. That means I need a formula. I need a formula for the volume of this little slice as a function of x. Right? If x is all the way over here at 0, then that radius is 0, right? Because I'm at the very tip of the cone. And if x is all the way over here at the end, then that radius is r naught, the radius of the base of the cone. So the question is, can I find a formula for the radius, this radius, as a function of x running from 0 to r naught? I'm sorry, running from 0 to h. So h is that x value there. Of course, 0 is at the origin here. The game is that v will be the integral from 0 to h of my little differential volume. And I know that that little differential volume is 2 pi times the radius dx. So the only thing that I'm missing here, the only thing that I don't know that I need to know to calculate that integral is how that radius changes as x runs from 0 to h. Bunch of ways to do this. You can do this using similar triangles. You can do this by saying, okay, this function right here must be a linear function, right? And the radius is clearly just the y value on that along that line. I'll take the similar triangles approach, but I'm kind of thinking of this as a pure geometry thing. Let me write down what it is we're looking for. Pull myself up here. Yeah, okay. So we need to find r. Let's say note. R equals r of x is a function of where we take the slice. I think it's fairly obvious that r is a linear function of x, right? Because r is just the y value along this boundary here, which is a straight line, because we're talking about a cone. But because this way of thinking will be useful to us in other places. I'm going to get there by similar triangles. I'm just going to draw the quadrant 1 portion of this picture. And I'm going to draw it in 2 dimensions to make life a little simpler. Here's H, that's the height of my cone. I'm thinking of X. X is being here. And I have this very narrow strip. Right there. And my radius, the thing that I want so desperately, is this. So who's familiar with what similar triangles are? Anybody remember that concept from geometry class or trigonometry class?
They can be different sizes, but like the proportions are the same.
Precisely, yeah. Right, 2 triangles are considered similar if the ratios of side lengths are the same, or equivalently if they have the same internal angles. So here's a big right triangle, and it has a little right triangle inscribed within it. Since this is a 90-degree angle, ding ding, this is a 90-degree angle, ding ding, and this angle in here is shared between the 2 triangles, the big one and the small one, the big triangle and the little triangle must be similar. In other words, the ratios of side lengths are the same. Let me include this label here. This is R0, the radius of our cone's base. So by similar triangles, the ratio of side lengths of the big triangle is the same as the ratio of side lengths for the little triangle. So what are the side lengths of the big triangle? Well, I don't know this hypotenuse, but I don't give a shit. I'm only after this radius. So what I can do is compare this radius over this line to this radius over this line. I know that little r over x is equal to R0 over H. Right? It's like saying that because these 2 triangles are right triangles with the same angle here, they have the same tangent. Right? Opposite over adjacent to the big guy is the same as opposite over adjacent to the little guy. Again, I seek R as a function of X. R0 and H are constants. So if I just multiply both sides by X, I have what I want. So this is equivalent to saying R is equal to R0 over H times X. And that is R as a function of X. And that's the only thing I was missing in setting up my integral here for the volume. Therefore, the volume of my cone is the integral from x equals 0 to x equals h of dv, the volume of the slice. And I think of that slice as sliding through the cone from over there at the far left where x is equal to 0 to over here at the far right where x is equal to h. That dv is 2 pi r dx. So this is the integral from 0 to h of 2 pi times my radius, which is R0 over h times x dx. And I just want to stop here for a minute because this is certainly the bulk of the work. Concept questions first. How do we feel about the idea of the slice moving through the cone? Is that making sense? Kind of the fundamental idea is that for every x value between 0 and h, there is a slice like this. And if I know the volume of all those slices, I can add them up to get the volume of the cone. The integral is precisely the tool that adds those up. And dv is the volume of that slice as a function of x. If x is way over here, then dv is very small. If x is way over here, then dv is about this area, right? 2 pi r0 times dx. And it changes as we move through here. So it's not constant. The way we get at it is by imagining the slices being at an arbitrary x location. And you think of x as a variable, then you can get a formula for all of them at once. How do we feel about this similar triangle? Any questions about this stuff? Okay, then let's do our integral. So 2 pi r naught and h are all constant. They'll come out. We have 2 pi r naught over h times the integral from 0 to h of x dx. The integral of x dx you guys could have done months ago. This is not challenging. X squared. And we evaluate from 0 to h. Oh. Oh my goodness, I've done something terribly stupid. I'm so sorry. I'm so sorry. What's the area of a circle?
R squared.
Yeah. Yeah. All right. So let me pan my Zoom folks back over here.
That's circumference.
Yeah. Yeah. I gave you the circumference here. We need the area. The area of the cross section, the area of the circle. I'm thinking this isn't going to come out how it's supposed to. What did I do wrong? The area of the circle here is pi r squared. I'm thinking ahead to the next method. So this is not a 2 pi r. This is a pi r squared. I'm so sorry. This work is fine. 15, 16. Oh. So, pan my Zoom folks back, right? The area of the cross section is not 2 pi r, it's pi r squared. Please make that correction here and here. I'll pan you back over to make the corrections on the other side. Triangles work is fine. Nothing wrong with this. But dv is pi r squared dx. For the rest of this change. The integral is still an easy integral. Okay. So it will not. All right. So this is pi times my radius function squared. So that's r naught over h times x all squared. Right. Pi r squared, that r is this r. So in our integral, dv is pi r squared. So pi times my radius squared. The constants that pop out are different also. So let's. All right, the pi will still come out. When I square r naught over h times x, I'll leave it in for this line. It's going to be pi r naught squared over h squared times x squared dx. Right, it's a product here and a quotient here. You can just square each of the terms. Now what's going to come out is a pi r naught squared over h squared. And then what's left is integral of 0 to h x squared dx. And this is no harder an integral. One third x cubed. when you plug in the lower bound 0 here, 1/3 times 0 cubed is 0, so there's no contribution from that. When you plug in the upper bound, this will be 1/3 h cubed. I still have my pi r0 squared over h squared here, and then we'll multiply by 1/3 h cubed. And there's some cancellation between the h squared downstairs and the h cubed upstairs. I r0 squared over 3, and then h squared downstairs, h cubed upstairs, just gives me h. And that's it. If you heard that formula from geometry before, right? 1/3 pi r squared times h. This is the dishwasher method or the slicing method. This we would call a slicing problem because we're not really thinking of it as a solid of revolution, but it certainly can be achieved that way. This is the disk in the dishwasher, right? So the name of each of these methods comes from the little differential solid whose volume you integrate to get the whole volume. Okay, questions on this guy?
Does the age of the top of the column have anything to do with the age of the graph?
It does, yeah. So here I'm labeling h as like the height of the cone.
Mhm.
And here I'm just labeling that as the x location, right?
Okay.
So this is to help us see the bounds. We would integrate from 0 to h. But certainly, yeah, they're the same number.
So if we get a problem with this in a test where it seems like we're proving it in a way that's the formula.
The closest thing to a nice formula here is this. So at the end, I will summarize the formulae for you kind of in the cleanest way possible. There are formulas you'll find if you Google in terms of like the boundary function, but I really caution you against using those because if I move that axis of rotation around, those formulas are complete. But I'll give you the closest thing I can to like a general formula. Your starting point is usually this: dv equals pi r squared dx and the picture.
Or is it possible to just for like say like the radius is increasing and it decreases and increases?
Sure. Yeah. We can use this for all sorts of solids. In fact, let me go ahead and introduce the next portion here. So the cone is sort of a boring example, right? Because you have a formula from geometry already you could use. The technique is nice because it works on many more exotic shapes. So in general, here's how we're going to do it. I can apply this technique to any solid of revolution. And by solid of revolution, what I mean is a three-dimensional object you get by starting with some boundary curve, which could be anything, call it f of x. I focus my attention over some interval, say a to b, and then I rotate this thing about some axis. So I have a region here.
Can you move the camera?
Sure. Okay, so the sort of general approach is going to be, I give you some curve and an interval from a to b, a pair of x values, and then an axis of rotation. So for now, let me assume that my axis of rotation is the x-axis. So simplest possible case. If I were to take that green region and spin it around the x-axis, this thing is going to sweep out a volume. Imagine this like as a card or something comes out of the board and then back into the board and spins around. It's going to generate a solid. Solids, I don't want to say they could have any shape, that's not true, but any shape with rotational symmetry is achievable pretty much. kind of your solid here would look like this. My 3D drawing skills are not the best in the world, but if it's like that, then this one should be this one. So flower vase or whatever, right? There's lots of shapes you can get this way. Spheres and ellipses or ellipsoids can be achieved this way by rotating circles and ellipses. And to get the volume of this thing, is come in here and draw a little differential thickness strip perpendicular to the axis of rotation at an arbitrary x value. X. That little strip, if you were to rotate just the strip, forget about the whole rest of the region, just rotate that strip, you're not going to get this whole solid, you're going to get a slice of the solid, which is a disk, hence the name. So rotating just that strip yields just this little disk whose volume we can calculate using the same trick, cross-sectional area times the radius. Again, you can think of that big solid as being infinitely many of these very, very narrow disks all stacked up together. And so if we're being careful, technically this would have flat edges, but the idea is that with enough of them being narrow enough, it doesn't matter that the edges are flat. If I focus my attention just on this little solid, I'll always call this little volume, I'll always call dV. In order to find that little volume, just like in the previous example, I need the radius and the thickness. The thickness of this solid is the thickness of this little strip, which is dx, because the strip is a vertical strip, its thickness is a little horizontal thickness or a small change in x. And the radius is just r, so this would be pi r squared dx, and this is the general disk method. It's also quite possible that your axis of rotation was not in contact with that green region, right? If that axis of rotation, if there's a gap between this region and this axis of rotation, then this thing would have a big hole running through it. And that would yield a little solid here that has a hole running through it, and we call it a washer. That's the washer in this washer. All right.
It's the little section you're drawing, is that just to like help us visualize it kind of, or does it play like an important role in calculating things?
Well, so I like to draw this. Every time I solve the problems, I'll draw this. I don't usually draw this. But yeah, here just to help you visualize. So this is the portion of the solid coming from our strip. All right, so every part of that green region generates a part of the solid. And what I'm doing there is highlighting the part of that solid that comes from our strip.
Yeah.
All right, so let's try something a little more exotic. I would love to cook up the volume of a sphere for you, but unfortunately that leads to an integral that we're not ready to do yet. Requires some tricks. We can find something else that's quite manageable. Let's do Let's see if we can find the volume. These problems tend to be quite wordy. Find the volume of the solid generated by rotating the region bounded by y equals e to the x and y equals 0 from x equals 0 to x equals 1 about the x-axis. So this is the kind of standard phrasing for one of these problems. This particular problem is not hard. But for first problem, you can do it. I just want to introduce you to the kind of steps. Step one, always sketch the graph. Right? Sketch and shape the region. So we need to know what my region is I'm talking about. E to the x, a curve we should all know well. Nice and gentle. It's sort of growing exponential. Right? There's a horizontal asymptote over here, y equals 0, that approaches its exponents obviously negative infinity, but that's not relevant for us. Goes to the point 0, 1. And let's scale up my horizontal axis just a little bit. I'll say 1 is here. So I'm interested in the region bounded by this curve and y equals 0. Y equals 0 is the x-axis from 0 to 1. So my little region, this region. First, sketch the region. Right, graph the function, identify what region you're talking about. Sometimes you'll have multiple boundary curves. Sometimes you'll have one boundary curve and a set of x values. It's up to you to determine the region. Next, sketching your axis of rotation. Right, here we said we're rotating about the x-axis. Okay, sketch the graph, shade the region, sketching the axis of rotation. Next, the strip. Bed marker is pooping the bed. We'll switch to pink for the strip. The strip for the disc washer method, which is the method we're using here, is always drawn in perpendicular to the axis of rotation. It's important. Strip is always drawn perpendicular to the axis of rotation at an arbitrary location within your region. So you don't want to draw it over at one end or over at the other end. You want to draw it somewhere kind of in the middle, and always with the understanding that it is at an arbitrary location. Now, imagine rotating just the strip. Right? These steps work for all of these methods. If I rotate just that strip about that axis, I will generate a little solid looking like this. That little solid has the little volume I need to integrate to find the volume of the total solid. This thickness is dx, right? The width of this strip is dx. I need also the radius of this little disc. Can anybody help me with the radius here? I'll tell you what I like to do. Remember, this little disc is coming from rotating this strip. So I like to come back to this picture and label all the geometry things in this picture. So if this strip is to pop out the board and rotate around like so, the disk generated as a radius coming from this height. Right? And if I take this marker and I spin it around, it sweeps out a disk in the air. The radius of that disk is the length of this marker, right? If I take this strip and I spin it around through the air, the disk it sweeps out the radius that is the length of that strip. The other thing that's often useful, can you characterize this point on the curve? Its x coordinate is x. What's the y coordinate?
E to the x.
Good. It's an arbitrary point on the curve y equals e to the x. So that ordered pair there is x comma e to the x. So with that in mind, you can tell me this radius.
Just e to the x.
Exactly, right? Down here at the base of the strip, this is y equals 0. This is the x-axis. Up here at the top of the strip, this is the y value of this point, which is e to the x. So my radius, here, my little radius is e to the x, which means my little differential volume is pi r squared dx. That's the area of this little circle times the thickness, which is pi times e to the x squared dx, or pi times e to the 2x dx. Once you have dv, you're golden. You just integrate dv to get v. The bounds you might want to think about a little bit. In order for this strip to move all the way through this region, x has to go from 0 to 1, right? So your bounds here are going to be the smallest x value in your region up to the largest x value in your region. So your volume is the integral from 0 to 1 of that little differential volume, dv. That's the integral from 0 to 1 of pi times e to the 2x dx. Pi is a constant, it will pop out. Pi integral to 1 e to the 2x dx. And this is one of those micro u subs that we talked about last week. So what is the micro u sub we would do here? Good. Yeah, if I had to do this, I had to do this integral in all of its detail. I would sub u equals 2x. In general, I think we talked about the version of this for sine and cosine last time. Micro u sub in this thing will yield a factor of 1 for a. Right, this is one of those that you just want to be able to do quickly. Yeah, it's like the derivative of e to the 2x is 2 e to the 2x by the chain rule. The integral of e to the 2x is 1/2 e to the 2x by micro u sub backwards chain rule. So I get pi over 2 e to the 2x evaluated from 0 to 1. All right, the 1/2 can pop out. Evaluating at 0 this time does give me something, so I'm going to be a little bit careful. At 1, I get e to the 2 times 1, which is e squared, minus at 0, I get e to the 2 times 0, which is 1. That's about as nice as that's going to get. Any questions on pen back over this? No, I'll leave it for a minute. Any questions on the integration? Any questions on the graph, drawing the strip, finding the radius? I don't have a problem telling you this. A question that shows up on my exam one every time. Here's a region, right? Boundary curve, blah, blah, blah. Sketch the region, set up the integral for the volume. Don't even calculate the integral. Just draw me the damn graph and label things appropriately. I can't tell you how often people totally bomb that. Don't be that dude, right? Make sure you're comfortable graphing. As you go through the problems in WebAssign, it's so important that you graph them by hand. Don't lean too hard on technology there. It's a skill you must have. And it's not just to the test, right? And maybe something will help. The reason it's so important for you to graph things by hand and to know what the graphs look like ahead of time isn't so you can draw the stupid graphs on my test. It's so that when you see a function, you can estimate its behavior in your head. When you see a function written down algebraically, I need you to know, oh, this is a fast growing function. Oh, this is a function that's always positive. Oh, this is a concave down function, right? Those sort of things are going to be really, really helpful. Not just in this class when we go on deeper into infinite series and stuff, but in your top 3 class and differential equations elsewhere. You want to think of these functions as your friends. Each one's a little dude and they have some behavior and temperament and stuff. And the more you know about them, the quicker you'll be able to kind of check your intuition. Yeah.
For the micro use of thing, like, do we have to make any indication that we are aware of that or something? Or is it, will that like, is there something that you could do?
If you
Or
just
something
give me the
don't-
black here, 10 out of 10 perfect.
Okay.
I would not give you a hard time for that. Anytime the differential is constant, right? I'm fine with you issuing the work on the U sub entirely. So here dz would be 2 dx, right? Anytime that differential is just a constant times dx, I don't see no. Okay. So solids of revolution and the disk method. If you apply the same logic to a region where there's a gap between the region itself and the axis of rotation, you'll yield something called the washer method. This last guy, e to the x from 0 to 1 rotated. E to the x from 0 to 1 gives me a disk. I rotate about the x-axis. So when I took the curve that we were just working with, y equals e to the x, the region from 0 to 1 bounded by that in the x-axis, rotated about the x-axis, I got a disk. If I were to move that axis of rotation down a little bit, maybe it'll help to also sketch the full solid here. Right, so the volume we just calculated was the volume of a solid looking like this. Right. If you rotate that green area, you get something looking about like that, very silly lampshade. If I were to take that same curve, same x values, so same region, but instead of rotating it, instead of rotating it about the x-axis, rotate it about the line, for example, y equals negative, let's say, -2. Actually, I'll draw a solid line on. I don't know, I usually do dotted. If I were to rotate about this horizontal line down here instead, I get a very different 3D shape, right? I would no longer be getting this thing. If I take this green region here and I rotate it about the line way down here, then the resulting solid is going to have this big gap in it. Do my best to draw it here, but no promises that this doesn't suck. On with that, right? So let's see this portion. All right, if I were to take the picture on the bottom and do the rotation, I would get this sort of a shape here, which is one, considerably more complicated, right? But two, and most importantly, has this big tunnel running through it, right? And the little differential solid that I would be thinking of this as made up of stacks of would also be quite different looking. Procedure is the same though. Drawing a little strip. Now imagine rotating just that little strip. If this little guy is going to come out of the board and rotate around, and I will have something looking make it a little smaller. About like this. This washer shape. Yeah. Kind of visualize it in here like this. Here's your gap, right? So we know that the little differential volume here, dV, is pi r squared dx. The little differential volume here is slightly more complicated. One way to think of it is as a big disk that's had a hole punched out of it that is also disk shaped. And I think maybe that's the easiest way to do it. If I label two radii now, little r and big R being the distance from the axis of rotation out to the far edge of my solid, and little r being the distance from the axis of rotation to the inner edge of my little solid, then this differential volume is the big differential volume, or the volume associated with the big disk, which is pi times big R squared dx, minus the piece I've punched out, which is pi times little r squared dx. And if you factor the pi's and the dx's, this is the same as pi times big R squared minus little r squared dx. So up top is a disk, down here is a washer. You get washers when there is a gap between your strip and the axis of rotation. As is the case here, right? Here in the first picture, my strip goes all the way down to the axis of rotation and the bottom of the strip sits on the axis of rotation. Here, my strip goes down to the line y equals 0, but my axis of rotation is the line y equals -2. So the question is, can I come up with the big R and little r without drawing these like wicked complicated pictures? And the answer is yeah, you can do it all in this setting, and that's what you want to do. You want to do it all just here with the graph of the region. You don't want to have to draw the pictures. And in fact, drawing the big pictures isn't especially helpful. Right? The axis of rotation runs right through the middle of this thing. So little r, right, and your strip, you can kind of think of your strip as being right here. Little r is the distance from the axis of rotation to the near end of the strip. Big R is the distance from the axis of rotation to the far end of the strip. I'll put it here. Since we have a specific curve, I can actually tell you what those are here. Maybe I'll ask you to help me. What is little r? What is the distance from that axis of rotation to the near end of the strip? It's 2, yeah, it's constant. And that's reflected in the fact that this kind of punched out cylinder here is constant in radius. So the vertical distance from the ass end of the strip down to the axis of rotation is 2. Okay, what is big R? I'll just leave these here like this. No. So little r in this case is 2. Big R in this case is what? We're good, right? I know that this vertical distance here is e to the x, right? It's the y value on this curve, y is e to the x. I know that this distance here is 2. So the total distance is 2 plus e to the x. This kind of making some sense. If you want fancier pictures, they can be fancier, but I'm not an artist, so I'm not going to try too hard. I don't know, that's even the wrong perspective. I'm bad at drawing 3D stuff. I'll just okay, if I wanted to find the volume of this big solid, we could do that by integrating. But I think it'd be more fun to work with a fresh curve. So let me summarize what we have here. We're doing a new problem, a fresh problem. And then we'll get the summary. Did I save that in? Can I just load the damn PDF? There. Let's grab something a little challenging. That's fun. Let's do something more fun. Something that gives us a wash. Here we go. All right. So what I'd like to do now is find the volume of the solid obtained by rotating the region bounded by the blah, 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 blah. Y equals x cubed, y equals 1, x equals 2, about -3. So I'll write it down on the front board here. In general, okay, find the volume, blah, blah, blah. Like this one. X equals 2, about -3. Okay, so these are your boundary curves, right? These are the things that determine your region. And then this is your axis of rotation. So I'm going to sketch my boundary curves, try to identify the region, sketching the axis of rotation. Y equals x cubed, looks something like this. A horizontal tangent and back out. Y equals 1. Horizontal line. Let's say that that is y equals 1. X equals 2. Let's see. Well, if this is the point on x cubed that goes to the line y equals 1, what is the x value there?
One.
Yeah, right. 1, 1 is the point on y equals x cubed. That intersects with the line y equals 1. X equals 2, therefore, is over here. X equals 2, of course, is a vertical line. And then the line y equals -3 would be down here. So sometimes it takes a minute to even recognize your region. Triple check and make sure I got everything right. Hi, this is a neat challenge. You know what? They didn't list this as one of the boundary curves, did they? So initially, I was thinking this region. What do you guys think? Does anybody see another possible thing that could be our region? I'll tell you, this can't be our region because they didn't tell me y equals 0 is one of the boundary curves. Right, so it has to be a region enclosed by the curves they did. So x cubed 1 and 2, x equals 2.
So it's just down to -3.
No, because this is also not a boundary curve. I'll tell you, I'm gonna have to redraw this. And the standard thing, right? Usually we end up drawing it twice, once to get an idea and then once to actually focus on the region.
Is that top right going to intersect?
Yeah. So I'll leave this, right? This is our first sort of sketch, trying to get an idea for what my region is. This is the general experience. You draw it once. You redraw, zoom in, question. So the big game is these guys, right?
Mr. Filesticker,
Yeah.
can you move the camera over because I can't see the problem you're working on right now?
Oh, that's a problem. Yeah, thank you. Sorry, I thought it turned over. All right. So we
Thank
said
you.
we want to find the volume of the solid obtained by rotating the region bounded by the curves y equals x cubed, y equals 1, and x equals 2 about the line y equals -3. And then I did a rough sketch of those curves here. And we realized that this, which at first looked like it might be the region enclosed by those, cannot be because they didn't say that the x-axis was one of our boundary curves. So if we're thinking about these curves, y equals x cubed, y equals 1 and x equals 2, the only region they could possibly enclose is the kind of pointy region here. So we're going to redraw the picture, helping us see that pointy region. There's y equals 1, there's x equals 2. And then my curve is x cubed. Like this. It's a little steeper here, so it should be quite steep. So here is my region. Right? Here's my region. And we're rotating about the line y equals -3. Sketch your boundary curves, identify your region, draw on the axis of rotation. Next step, draw the strip. Strip always goes perpendicular to the axis of rotation and always at an arbitrary x value within my region. Here's my little strip. Its little thickness is a dx thickness. And I need to find my inner radius, little r, and my outer radius, big R. In this case, it looks like the gap here is much larger than the thickness of the washer ring, right? This gap is quite large compared to the height of that strip. I can label the radii. Little r, distance from the near end of the strip to the axis of rotation. Big R, the distance from the far end of the strip to the axis of rotation. And it is helpful to characterize this point and curve. This is x, x cubed, because we're along the curve y is x cubed. I know it's a lot to draw, but you really do want to do this. This is the game. This is how we set it up. dv pi minus big radius squared minus little radius squared dx. So what is the big radius and what is the little radius? That's the question. Let's do a little radius first. Anybody help me with this little radius, little r? Yeah, it's 4, right? The vertical distance from -3 up to the x-axis is 3. And the vertical distance from the x-axis to that lower boundary curve, which is a constant, is 1. So little r is 4. What about the big radius?
4 plus extra.
Almost. So this distance here from the end of the strip to the x-axis, that is x cubed, right? This distance here is just 3. So it'd be 3 plus x cubed. Everybody following that? This is the x-axis. So to get from here to here, that's 3. To get from here to here, that's x cubed. So plugging those things in, and integrating, b is the integral of dv. The other thing you need to think about are the bounds. I'm integrating from where to where?
Oh, -3 to x.
My bounds should definitely be constant.
1
On the 2 is good. Yeah. So this point right here, from the smallest x value in my region to the largest x value in my region. That's the way it works. So the smallest x value here is 1, because that's where y equals 1 and y equals x cubed intersect. And the largest x value is 2. This would be the integral from 1 to 2 of dv. And dv is this thing with those plugged in. So that's the integral from 1 to 2 of pi times big R squared, which is 3 plus x cubed squared, minus little r squared, which is r whole squared. Yeah. So this problem can get a little gnarly, right? They can. The key is a good picture. Don't hesitate to draw your picture 2 or 3 times until you're happy with it. Once you have a good picture with plenty of space to label things, then you're ready to start finding distances and building up your integral. Once you have this, though, you're home free, right? This is a polynomial. Worst case, you got to do some algebra. I'll continue that down here. The pi can come out. Integral 1 to 2. If I FOIL out 3 plus x cubed all squared, that's 3 squared, plus 2 times 3 times x cubed is 6x cubed, plus x cubed squared is x to the 6. So that's 9 plus 6x cubed plus x to the 6. Minus 4 squared is minus 16. Yeah. 9 minus 16 is -7. This is pi integral 1 to 2. I'll write it in order like this: x to the 6 plus 6x cubed minus, what did I say? 7? Yeah, -16 plus 9. Yeah. No, we're just integrating a polynomial. It's just powerful stuff. This is pi x to the 7 over 7 from this guy. 6x to the 4 over 4, which can be rewritten as 6/4 is 300. 3 times x. 7x 2.
The upper bound.
From the smallest x value in this region to the largest x value in this region. So this boundary curve is x equals 2. Or you can think of this point up here. Is 2, 8, where x cubed and the vertical line x equals 2 intersect. So this point down here, 1, 1. I go from the smallest x value to the largest x value. So let me go over here, finish. At my upper bound, I'll have 2 to the 7 over 7 plus 3 times 2 to the 4 over 2 minus 7 times 2 is 14. And then from that we subtract 1/7 plus 3 times 7. And this can be cleaned up. 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128. 5 times 128 sevenths. 2 to the 4 is 16, divided by 2 is 8. So this is 3 times 8 is 24. minus 14. And I'm distributing this negative at minus 17 minus 2 plus 7. So what are my integers? I've got a minus 14 plus 7 is minus 7. 24 minus 7 is 17. So this, and this makes 17. I have 128 sevenths minus 1 seventh is 127 sevenths. And then minus 3/2. Up to you if you want to take it further than that. Honestly, I would accept this. Give me this on a test, that's fine. Give me this on a test, that's fine. Give me this on a test. The only thing I would give you shit for is the fact that 2 to the 4 and 2 is cancellation here. So that's always really cleaning up what to be done besides fraction arithmetic. And what I really want to see is that you draw the picture well, you set up the integral correctly, you take the correct antiderivative and reevaluate it correctly without making optical mistakes.
So as long as like the numbers are clear or whatever, like not in a square or square root form or something.
Pretty much, yeah. Every time I solve a problem like this, I'll do my best to be like, here's the step where you could stop, and I will be okay with it. The only reason I wouldn't give full credit for this, it's not that we haven't found 2 to the 7 or 2 to the 4. It's that 2 to the 4 and 2 down here cancel. So if you rewrote this with 2 cubed here and the 2 gone, 10 out of 10. No problems with that. I do not want to bust your balls up there, right? Everybody in the world has calculators. Right? This is not an arithmetic class. I think we're just about out of time, so let me give you a small preview of where we're going next. These problems can also be done sideways. Like the area problems discussed last time. So WRT means with respect to. These problems can also be worked with respect to the variable y. And sometimes that is necessary. So in the few seconds we have before I have to run, let me set something up like that really quick. I could say find the volume. Blah, 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 right, of the solid found by rotating the region bounded by blah, 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 blah. Let's do y squared equals x equals 2y. Sorry, x equals y squared, x equals 2y. About the y-axis. So the way I described coming up with dv, right, drawing the picture, drawing the strip, finding the distance from the near end of the strip to the axis of rotation, far end of the strip to the axis of rotation. That's really the way you should think about this rather than any bank of formulas, because a little change like this can really alter the geometry. The steps do not change. Sketch the region. X equals y squared. That's a parabola turned sideways. X equals 2y, you can think of as y equals 1/2 x, right? Straight line looking something like this. You see the region. We're going to solve this whole problem. I might recommend redrawing this again because the way I've drawn it here, that region is a little small and a little hard to work with, but we can do this. Sketch the curves, identify the region. What's next?
Drawing the
Before that, axis of rotation. So here I'm rotating about the y-axis. But yeah, now that I have all those things, I draw my little strip in. Should this strip be oriented up and down or left and right? Good, perpendicular to the axis of rotation, always for the disk washer method, perpendicular to the axis of rotation. So here is my little differential thickness strip. And you notice that the thickness of that strip is no longer a little horizontal thickness, but a vertical thickness. Right? So this thickness here is a dy thickness. If I rotate just that strip, put it down here. I will get a solid that looks like this. I take this strip and spin it around here. Get something looking like that. This is a dy thickness, still has a little inner radius and a bigger outer radius. I can label those here. Bigger outer radius is still the distance from the far end of the strip to the axis of rotation. Little inner radius is still the distance from the near end of the strip to the axis of rotation. I'll finish up here just by saying what dB is. So little r, big R. Since the thickness of the strip, or thickness of this washer is a dy thickness, everything here will need to be done in terms of y. Right? This means my integrals can have a dy at the end, so all the variables inside have to be y's. So I need big R and little r as functions of y. Little r is the horizontal distance from the y-axis to the x value along the curve x equals y squared. And characterizing the points on the curve, very useful. This point right here at the near end of the curve is y squared comma y. This little point over here is 2y comma y, right? Because this linear curve is x equals 2y. So the x coordinate is 2y and y is the independent variable. This parabolic curve right here is x equals y squared. So the x value there is y squared. And again, y is the independent variable. So what's little r? What is the horizontal distance from the y-axis, which is my axis of rotation, to the leftmost part of that strip?
Y squared.
Very good. All right. The x value here is y squared. The x value here is 0. So this is y squared minus 0. Or just y squared. Okay. What is big R?
2y.
Very good. Same logic, right? X value here minus the x value here. That's 2y minus 0. Therefore, dv is pi big R squared minus little r squared dy this time, right? So my thickness is a y thickness, which is pi times 2y squared minus y squared squared dy. And then the last thing you would need to do is find your bounds. We would integrate here from the smallest y value in the region to the largest y value in the region, right? I think of this strip as moving through this region now. The smallest y value is 0. We need to know the y value up here where 2y and y squared touch. So if you set 2y equal to y squared, put this over here. If 2y is equal to y squared, that means 0 is equal to y squared minus 2y factorial y. We get y times y minus 2, so y equals 0 and 2. So that's the integral from 0 to 2 of pi times bracket, big paren, 2y squared minus y squared squared dy, like this. You can see similarities to the area problems, right? Sketching regions, drawing strips, thinking about bounds, it's all the same. The only difference is now you have to also think about this axis of rotation and the distance from the near end of your strip to that axis of rotation, the far end of the strip to the axis of rotation. The closest thing I can give you to a formula. And I'll do this again on Wednesday after we talk about the cylindrical shells method, and I'll contrast the two. Closest thing to a formula that will never let you down, right? If you bank on formulas you find on the internet, they will let you down. Formula procedures. Fifth region. Rotation. All the strip. Does everybody know what this symbol means? Upside down capital P. Red perpendicular. To the axis of rotation. And then you're going to integrate dv equals 5 times big R squared minus little r squared. I'm going to write dt, where big R is the distance from the far end of the strip to the axis of rotation, which may not be a coordinate axis. And little r is the distance from the near end of the strip to the axis of rotation. And finally, dt is either dx or dy, depending on geometry, right? It's the thickness of your strip. So if your strip is oriented vertically, the thickness is a horizontal thickness and dt will be dx. If your strip is oriented horizontally, then its thickness is a vertical thickness and dt will be dy. This is as good as you can get for the formula here. And this is for the disk washer method. I'll contrast this with the cylindrical shells method next time. The difference between the disk washer method and the shells method: disk washer, strip goes perpendicular. Ask yourself what would happen if I drew the strip parallel to the axis of rotation. The little differential solid will have a different shape. So you'll end up with a different formula for the little differential volume, but you can kind of follow your nose to the same steps and get there. I'm not expecting you to do that. I'm going to publish a homework today, and what I am expecting you to do is work a couple 6.2 problems before class on Wednesday, just a few of them. Right, 2 or 3, there will be more than that, but work 2 or 3 of them before class on Wednesday so you get a feel for kind of this procedure, drawing tiny distances, what problems are easy, what problems are hard. Right. We've gone a little bit over, so I'm going to rush out. Is that a 10 sheet? Okay. You too. I'll see you in office hours this afternoon.
Yeah, it's 1 to 2, right?
Very good. Yeah, 1 to 2.
I'm in class at 2, like on campus. Can I like be